Hello, welcome back to Virtual School. Physics is fun. This is Puan Liao. Okay, we are going to continue with refraction of light, mainly refractive index. So what is this refractive index? So in simple language, it means how much light band, okay? How much light band in a medium is an indication of how much light band is called refractive index. Okay, so an indication of the ability of light to bend. So if the refractive index of a medium is higher, so the bending effects is more. So if it bends more, then therefore the refracted angle will be smaller. Okay, so as the refractive index, N stands for refractive index, N increases, it bends more, so the refracted angle R will be smaller. Okay, let's look at this picture on the left. You can see that light is refracted towards normal, okay? So angle of refraction is smaller than the angle of incident. So immediately we know that B is denser than A. So when we say B is denser than A, we actually mean optical density. Okay, so the optical density of B is higher than the optical density of A, and the refractive index of B will be higher than refractive index of A. So optical density and refractive index, they are closely related to one another. When optical density increases, refractive index increases. Okay, so this picture on the right shows that light is refracted away from normal. Okay, this normal is refracted away from normal. Therefore, we know that medium C is denser than medium D, which means the optical density of C is higher than the optical density of D. Therefore, the refractive index of C is more than the refractive index of D. Okay, clear? Let's look at refractive index further to enhance our knowledge. All right, this picture here shows the refractive index of air is 1 and water is 1.33. So immediately we know that water is optically denser than the air. So in an optically denser medium, light will travel slower. Okay, it travels slower, therefore it bends more. So in an optically denser medium, the refractive index will be higher, right? So like I said just now, when optically denser, the density, optical density increases, refractive index increases. So same here, air and crown glass. Okay, crown glass, refractive index is 1.52, which is higher than water. So if we compare crown glass and water, so air, a light will bend even more in crown glass compared to in water. And light travels even slower in crown glass than in water. So from here, we proceed to the definition of refractive index. So refractive index is defined as the ratio of speed of light in vacuum to the speed of light in the medium. Okay, look at this notation here. Refractive index equals to C over V, where C represents the speed of light in vacuum and V is the speed of light in that particular medium. Okay, so speed of light in the vacuum is 3 times 10 to the power 8 meter per second. Okay, speed of light in a medium will always be slower than in the vacuum. Therefore, N will always be more than 1. N will not take a value that is less than 1. Okay? Okay, let's look at some examples of refractive index. All right, you can see water refractive index is 1.33, acetone 1.36, glycerin, benzene, silicon oil, and sodium chloride. So they have their own refractive index. let's calculate the speed of light in water. So by using the formula that we have studied just now, N equals to C over V. So now we substitute the values in. So refractive index of water is 1.33. Speed of light in vacuum is 3 times 10 to the power 8. And V is the speed of light in water. So now we rearrange and we get V, the speed of light in water, is 2.26 times 10 to the power 8 meter per second, which is slower than the speed of light in vacuum. What about glycerine? Okay, using the same method, we get the speed of light in glycerine is 2.04 times 10 to the power 8, which is even slower. Alright, so that proves to us that as refractive index increases, the speed of light in that medium decreases. Okay, so it slows down even more. So it bends even more. Okay, so refractive index N is an indication of how much light bend. So the higher the refractive index, the lower is the speed. It will be slower and the bending effect is more and the refractive index is smaller. Okay, so as refractive index increases, speed decreases, refracted angle decreases. Okay, so now we add in speed. So as refractive index increases, speed decreases and the refracted angle decreases. Okay, let's look at this experiment called Snell's law experiment. Okay, we will need a ray box, a glass block, and of course ruler and protractor. So we have this incident ray at this incident angle, and we see that light is refracted as it travels into the block, in the glass block, and we measure the refracted angle R. We repeat this experiment with several incident angle, let's say 10 to 80, and we measure their respective refracted angle. After that, we calculate the incident sine of the incident angle and sine of a refracted angle. And we get that sine of incident angle divided by the sine of a refracted angle all gives us a similar value. For example, when I is 10, R is 6.5, so sine I over sine R, which is 0.174 divided by 0.113 gives us 1.53. But as I increases, R increases, but the ratio of sine I over sine R all they are all around a similar value. Okay, so from here we conclude that sine I over sine R is a constant value. And this constant value is called refractive index. Okay, so from here we get the second formula for refractive index, that is sine I over sine R. Right, refractive index equals to sine I over sine R. But don't forget, I must be in a less dense medium. The incident angle is in a less dense medium and the refracted angle is in a denser medium. Okay, let's look at this calculation. So we have light travel from air into this medium B. So what is the refractive index of medium B? As you can see that the incident angle is 53 degree and the refracted angle is 37 degree. Okay, so let's substitute into the formula N equals to sine I over sine R. That gives us sine 53 divided by sine 37. So answer is 1.33. Okay. The next question. This light is traveling from medium A to this medium, right? And you can see that light is refracted away from normal. So from here, we know that this medium, white medium here, is of lower optical density compared to A. Okay, so when we want to use Snell's law formula, so bear in mind I must be in a less dense medium, R in a more dense medium. Okay, so when we substitute into this formula, so we do not substitute wrongly. Yeah, so I is how much? 40 or 30? Remember, I must be in the less dense medium. So now I is 40. Okay, R is 30. Don't get tricked by the arrow. So it does not follow the arrow, but it follows this less dense to more dense. Okay, so sine 40 over sine 30 gives us 1.29. Alright, so the refractive index of this medium A is 1.29. Remember, n must be more than 1. Okay, what about this? We have light travel from air to crown glass. Okay, so the refractive index of crown glass is 1.52 and the incident angle is 60. So how much is this angle theta here? Okay, using the same formula, we substitute in and we get theta equals to 34.7 degree. Okay, all right. So Snell's law says that refractive index equals to sine I over sine R. In fact, this Snell's law is the second statement of the law of refraction. Remember, law of refraction, there are two statements. First statement says incident ray, normal, and the refracted ray all lie on the same plane. Second statement says is actually Snell's law. That is, refractive index equals to sine I over sine R. Okay. Alright, so we will stop here for today, and we will continue with other ways to calculate refractive index. Okay, that's all. Bye bye.